one's a sig fig thing.
So that's why it has to have all the.
Yeah, since like the lesson is sig figs.
That
Yeah,
makes sense.
otherwise I'm a good
Okay. Dang it. Alright, I just thought I'd ask.
All right, let's go ahead and get started. So do we want to do a few more conversion problems so we feel good about that? That was kind of the sense that I got. So let's just start a nice warm-up. Let's see. These first two, so 3 grams to milligrams, what's that? And then 7 meters to centimeters. So go ahead, work those problems out, get your brain firing. And then I would set it up using the proper dimensional analysis, even if you think it's easy. And I am watching the chat live, so if you're joining us remotely, ask questions as usual. Oops, uh-oh. Thought I lost my pen for a second. All right, what do we get for the first one? 3 grams to milligrams.
3,000.
So 3,000. Oh, sorry, give me 1 second. I don't understand how I use the same setup, but it likes to change my mapping settings. I apologize. There we go. No, I don't have a crazy sensitive. All right, I see 3,000 in the chat as well, so let's go over how we got there. So just start off with your known, and then we want to pick the correct conversion factor. So we could always reference this over here. So we were going grams to milligrams. So milligrams has a factor of 1,000. So we can say, so which one would we want on top then? So 1,000 milligrams in 1 gram, then multiply across to give us our 3,000 milligrams.
Why is it that it's set up that way instead of just multiplying by 1,000?
Yeah, I'm just being really explicit to write it like that so you can clearly see. And like, you know, just putting it over 1 really doesn't mean anything, but again, it lets us kind of set up that conversion factor.
So on that assignment, if we don't set it up that way, if we just put like 3 times 1,000, is it incorrect? Do we need to set it up exactly that way?
Well, you want to have some sort of like conversion factor, because the thing is, if you just write like 3 grams times 1,000, right? I don't know what that really means, right? But if you, the thing is conversion factor, it's telling you the relationship between milligrams and grams, and it could be anything, right? We're just using these nice units, but, you know, I could say there's 2,341 quarks in a floof, right? And then so that gives you your new conversion factor, your relationship, and then you can set it up appropriately. So does that make sense? And then when we do other mathematical things, so again, this is kind of simple right now, but we'll hit density in a second. And so density, you know, there's more mathematical manipulations, and keeping those units like that will kind of help you. So I know it seems maybe simple right now, but it will help you down the road to do it like this. All right, what about 7 meters to centimeters? So here is 700. And so again, we can do the same thing. So just setting what we start with, picking the right conversion factor. So there are 100 centimeters in 1 meter. Now those units cancel out to give us 700 centimeters. So let's move on for now. We can come back to conversion factors and converting. I don't know if anything came up in the homework in particular that you want to go over. We can. Let's look at some other stuff. So let's look at significant figures. So significant figures will come back to haunt you again and again and again. And so it's good to get these basics down. And so significant figures, they're really important, and we'll see this in lab, because they reflect basically how accurately you can measure something, right? So it depends on the precision of your glassware, it depends on your ruler, and how many like digits your balance gives. And so that's why we have to carry these significant figures appropriately, because when we report our number, right, we don't want to have too few or too many sig figs, because that could give us kind of a distorted picture. And then just as like a FYI, so conversion factors are treated as exact values, so we don't count them when we're looking at like trying to determine which one has the most significant figures. So anytime you have like a relationship 1 inch to 2.54 centimeters, you don't include this 1 inch and 2.54 as part of your sig figs as 1 and 3. you just look at the original number. And so we'll look at what that means. All right, so here's some significant figure kind of rules, but they should be fairly self-explanatory once we go through them. So the first rule is all non-zero values are significant. So that makes sense. So if you have a number, that means it's significant. So in this case, we have 536. They're all non-zero numbers, so we could say that that has 3 significant figures. The next one is what I call the captive zero rule. And so this also makes sense. So anytime you have a zero between non-zero digits, they're significant. So you have this zero trapped between these two non-zero numbers. So in this case, 6,703 has 1, 2, 3, 4 significant figures. So now we have our next rule. So now I call these order of magnitude. And so these are not significant. So if we look, you can have leading zeros. So these are placeholder zeros to the left of a non-zero digit are not significant. So that's kind of convoluted, but all this is saying, right, is these zeros are showing how small. So shows how small, and so that would be not significant. So anytime those zeros are just showing magnitude, so in this 0.0043, those zeros are just telling us how small that number is. And so in this case, the 4 and the 3 are the only 2 significant figures. So that only has 2 sig figs. Now our other magnitude example are trailing zeros. So now the rule says zeros to the right after a non-zero digit are not significant. So again, this is showing magnitude. So now this is answering how big. And so this number 7,000, so this would only have 1 significant figure since those 3 zeros are just showing how big. And then this next example, so 32,040. So this is a captive zero, so that's significant. And then this last zero is just showing how big that number is, so it is not significant. So does that make sense? So again, I'll highlight any zeros showing how big or small, not significant. And then the last rule is so zeros to the right after a decimal point are significant. And so I kind of call these unnecessary zeros. So, right, we didn't need to write 50.0, but this 0.0 here is indicating that, yes, we can actually measure that accurately to the 10th place. Maybe we put it on a balance, and this balance went out to the 10th place, or maybe it was a ruler, and we saw that it was exactly at 50 centimeters, so that's 50.0. And so that means that it has 3 sig figs. So now looking at this next example, so 0.0600, right? These 2 leading zeros, so those are showing how small, so those are not significant. But then these last 2 here, right, we didn't need to put them there. They're not necessary, they're not showing how big, how small. So what they're saying is, no, we can accurately measure out to this value. So in this case, these are significant, so that would be 3 sig figs. So let's look at a few more. Oh, actually, we'll look at the practice in a second. So let's look at the glassware precision before we look at sig fig practice. And so we'll do this in lab, but of course, if you're joining us online, you can see how to measure things. And so it all depends on your glassware, again, on how far you can measure out. And so in lab, you want to make sure that you get my help, especially if you don't know how to measure these or you're doing it for the first time, because it's not, that easy. And so looking at this glassware here, so let's zoom in on this. So this is a volumetric cylinder, or graduated cylinder. And so you would have to look at the markings here. And then you want to establish, right, kind of how many markings do you have from 4 to 5. So in this case, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they're standard, right, 0.1 milliliter for each line there. So you want to be careful because sometimes you have funny glassware that is like 0.2 milliliters per one, so that can throw you off. And then we want to read from the base of the meniscus here. I'm going to pick a different color. So we want to read right at the base, at the bottom of the meniscus. And when you're doing this in lab, so you want to get at eye level with your glassware. So you might have to like bend down, right, because you want your glassware to be at a flat surface. So you're going to have to get down eye level with your glassware to read it accurately. If you were doing like a titration, you might have to get a stool and like look. You want to be at eye level so you can tell. And then, so let's look at this. So we're at 4 point, well, we can tell it's between 4.5 and 4.6. And so we could estimate it. So we could take it out, so 4.5, so we know this for certain. And then we can guesstimate the last digit. So what do you want to put for the last one? So 4.56, you said? Well, we don't want to take it to 4.6 because then it'd have to be right on that line, right? So then we would say it's 4.60, which you could write that, right, if you thought it was right there. Oh, what might be another guess? Because to me, it doesn't look like it's quite at that 6 line. So we could go, so 4.59, right? But then this is your last digit, right? So you have uncertainty there. And that's fine, right? So everyone's going to have different answers. Someone could disagree, right? You think it's 4.55, whatever. But this is, again, the point of our significant figures is that we have 3 sig figs here with this measurement. There's uncertainty in that last digit, again, just from the precision of our glassware, and so that's going to affect all our measurements and how accurately we can calculate like the density or volume, all those good things. And so they came out with 4.56, but again, you could argue whatever. All right, so let's look at these examples. So I'll give everyone just a minute to kind of mentally go over them, and then we'll go through them. So how many sig figs are in the following 5 questions? So again, take a minute or so. I'm watching the chat too for answers or thoughts, questions. the chat has answers. So let's start going through them. So number 1, how many sig figs does it have?
2.
So I hear 2. Thumbs up in class. All right, so 2, exactly. So we have these first 2 numbers are significant. These other zeros just show how big. So 2 sig figs, exactly. And chat is all over it as well. What about number 2 here, 304? How many significant figures?
3.
So we got 3 here, right? So don't let this captive 0 trick you. So, right, the 0 is stuck between those 2 digits, so they're all significant. So 3. What about number 3? So we have 0.00000210. So 3, exactly. And chat also has 3. And so that was really good. So all these zeros, right, they're just showing how small. So they're not significant. But then these are, and then of course that last 0, right, was unnecessary. We didn't really need to show that. So it is significant, and that must mean that we can measure that accurately. And then what about number 4? So 4,500,000. I see some 2s. Yeah, some fingers for 2s. I see 2 in the chat as well. So 2. So all these are showing how big. And then what about this last one? So I see fingers for 2, some 1. So this is a tricky one. So I did this on purpose to trick you. So the
Actually, 5.
no, we wouldn't go that crazy, but it is 2. And the trick is this little period here. And so sometimes you see, right, of course, if I had written 10 without a period, that would just be 1 sig fig. And this is not very commonly used because of the confusion that it causes. But as soon as you add that decimal point there, now it's stating, yes, this is actually significant. And so this would be 2 sig figs. Now, sorry, let me jump around for a second. So are you all familiar with scientific notation? Yes, no, kind of. So part of the trick, and we can review scientific notation more, but basically if you can rewrite the number in scientific notation and get rid of the zeros, that also helps you, yeah.
Isn't that what we did when we were talking about the conversions yesterday? And it was 1 times 10 to the exponent?
Yeah, like all this,
Yeah, isn't that scientific notation?
yeah.
Okay.
Yeah, so you've seen this, and so basically, if you can, convert this back to scientific notation, so we can write this as 1, 2, 3, 4, so 5.4 times 10 to the 4th, and so that's a much clearer way of notating that that has 2 sig figs. So same for number 5, if you wanted to indicate that it has 2 sig figs, it might be better to write 1.0 times 10 to the 1, which again seems a bit excessive for what we're doing, but at least in this case you can clearly see that, okay, I got 2 sig figs there. So does that kind of make sense? So now let's look at the math and probably the part that will haunt you for, well, the rest of your scientific career. But so we said that of course these measurements, right, dictate how accurately we can measure, and of course this dictates our answers. And so we have these rules for mathematical operations. And so the easy one is multiplication and division. So multiplication and division have the simplest rule. So the least precise measured value determines the number of significant figures in the reported answer. And so let's look at our example. So looking at this simple problem, so 3.56 times 4. So let's just do this all together so we can see. So, right, punching this into our calculator, we would come up with 14.24. But now we're looking at our numbers here. So how many sig figs do we have in 3.56? So you can give me hands so I see. So we have 3 sig figs here. And then how many from 4? So just 1. And this is where you have to be careful with your measurements in lab. So now, we can only report this 14.24 now to 1 sig fig. So it gets rounded all the way to 10. So does that make sense? So now let's look at this next one. So 2.050 times 5.0. So punch that in. We get 10.25. Now we have 4 sig figs from our first number, only 2 from our second. So now we have to round to 10 with 2 sig figs. And so that's where they say change it to scientific notation so you don't have that awkward decimal point. So we could rewrite it, again, that 1.0 times 10 to the 1 there, and then milliliters squared. And then so for division, same rules apply, so we punch it in, so 45.0 divided by 9, so our calculator spits out 5, except once again, right, we only have 1 sig fig from here, so we're limited to just 5 centimeters as our answer. And let's see, so this one, this is what we were saying that conversion factors don't count. So this is our initial number, right? And that has 2 sig figs. But now this is just a conversion factor. That's a conversion factor. This is a conversion factor. So we don't include those in our sig fig count. And so we just have 2 sig figs from our initial measurement of 4.5 feet. And so we do all this conversion, yada, yada, yada. And so we could round to 1.4 meters there. So any questions on multiplication, division? So that should feel straightforward. So addition and subtraction is a little harder, and I only say that because I feel like you have to write it out, you know, elementary school style to see it. And so for addition and subtraction, the value with the smallest decimal measurement determines your answer's significant figure. And so let's look at that. So now looking at this example, and again, this is why I say it's like elementary school, but it's easy to line it up that way. So we have 23.467 plus 313.21, and so let's punch that in. And of course, our calculator spits out that answer, but we're limited to 2 decimal places after the decimal point. So we can only report out to the hundredth, so we have to round, and so that gives us 336.68 for our rounding. And then, so this one's a little awkward. So we have 457 centimeters, subtract 0.68 centimeters. So punch that into your calculator. You get 456.32, but we have no numbers after the decimal place. So now we just have to round to 456 centimeters. And so, right, order of operation and all that stuff matters. And so just keep rounding till the end, but you have to like carry your sig figs, you know, through the multiplication and division. So report that, kind of your sig fig, and then if you have to do addition, subtraction, keep that separate. All right, so this is just a quick scientific notation recap. But it sounds like everyone is pretty good on that, so that was just showing how to go back and forth. I think everyone knows positive exponents means large numbers, negative exponents means smaller numbers, but I can slow down if people need it. So now let's look at our temperature conversion. So we have 3 main temperature scales, and so I think somebody said it last time, but what is the Kelvin scale based off of?
It's based off of the Celsius scale, except it's set at absolute 0 instead of freezing point water.
And so what is absolute 0? Do you know?
Essentially, it's a theoretical temperature where the molecules have absolutely 0 kinetic energy.
Precisely. So again, it's theoretical. I think they've gotten really close. I'd have to see like how close they've gotten now. But that's absence of all molecular motion, right? So we'll go into all the molecular motion, but usually you have electrons moving around. So even, you know, again, we have a solid here. It's not actually solid at the molecular level, right? Everything's vibrating, moving, but except at absolute 0, there would be no motion whatsoever.
Some really interesting things happen when you approach it that obviously I'm not going to get into. It's just a fascinating subject. That was my only internet. I apologize.
We can definitely discuss more fun facts after or in lab too, since I see all of y'all in lab. So what's interesting about the Kelvin scale as well and the Celsius scale is so they are just off by a factor of 273. And so that's an easy way to convert. So temperature Kelvin equals temperature Celsius plus 273. And I think it's technically 0.15, but the only time you really care about this 0.15 is on your homework question where it's like exactly this number. Because otherwise, when you're measuring a temperature, it's probably inaccurate anyways. And so we just use plus 273, but it's the only reason why I brought up that 0.15. And so, of course, they do increase at the same rate. So 1 degree increase in Celsius is also equal to 1 degree increase in Kelvin. Then, of course, we are more familiar with the Fahrenheit scale, at least in America. And of course we know, so water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. So that is a nice thing about the Celsius temperature scales, that it's kind of easy to remember. They set it at easy numbers. So water freezes at 0 and water boils at 100. So pretty easy, other than, you know, the random 212 degrees Fahrenheit for boiling. Of course, that being said, I can tell you what like great reaction temperatures are in Celsius, and I can tell you what nice degrees are on a sunny day, but trying to mix the two, I can't do. And then, so let's look at how you would convert between Celsius and Fahrenheit. So we have two formulas here, so I would write these down. And so we can go either our temperature Fahrenheit is equal to 9/5 degrees Celsius plus 32. And then, of course, rearranging that to solve for Celsius. So our temperature in Celsius is equal to 5/9. And then you'd have to do your subtraction first. So whatever your temperature in Fahrenheit is minus 32, do that, and then multiply by 5/9. And you might see this same formula just with whatever the decimal equivalent of 9/5 is, which so yeah, you might see 1.8 instead. So fairly simple there. All right, let's look at density. So this is some more math. And so we have this formula. So all density is just a ratio of mass to volume. So I should have said a joke. Well, the joke is, right, which weighs more, a ton of feathers or a ton of bricks?
It depends on if they're the same type of ton.
Well, what's the trick that you could have fallen for, but y'all are too smart to fall for? Exactly, but what are people actually thinking of? What problem?
Density.
Yeah, all right, so y'all are super on top of it, so exactly. So people are thinking of density, so of course, again, those feathers have a smaller mass to volume ratio. And so this is the math for it. I'm going to go ahead and show the triangle trick though. So we can rewrite this as density, mass, volume. And so why I like this little triangle trick is that if you ever get confused, it helps remind you what you're supposed to be doing. And so how the triangle trick works is you just cover whatever you're solving for, and we'll practice it in these problems. Well, let's say you wanted to solve for mass, so you can cover up mass, and then it tells you what to do. So you have density and volume next to each other, so then you would just multiply those two, and you would get mass. We'll also see how those units cancel. And then you could also, let's say you wanted to solve for volume, so cover up volume, and so what's left is mass over density, so that's what you would do, divide mass divided by density, that gives you out volume. All right, so let's look at this example. So if we have 73.2 milliliters of a liquid, and it has a mass of 61.5 grams, what is the density in grams per milliliter? I'll give everyone a minute or so. Let's give other people a second. I know some of you are Speedy Gonzalez's on your calculators. And so while y'all are plugging that in, so I just want to point out how you can still use your dimensional analysis because you're looking for grams over milliliters. So you could just kind of start with what you know. So you have 61.5 grams. And then we already know density is mass divided by volume, but you could also see, we can write it this way. So this is the same thing as dividing, right? I just wrote it this funny way to kind of prove that dimensional analysis works. So that gives us our proper units of grams per milliliters like it's looking for. And so what's the density? Somebody give me a number.
0.840.
So 0.840. So I see 0.9 in the chat, but I'm going to point out, so this is where our sig figs come into play, right? So we don't want to do any over rounding. So we have 3 sig figs for our milliliters, 3 sig figs for our mass. And so yes, our answer has to have 3 sig figs. So did everyone get 0.840? I can plug it into. And so again, don't forget your units, so grams per milliliter. Awesome. Thank you, chat, as well. All right, let's try another one. So again, give everyone like a minute or so. So determine the volume now of an object that has a mass of 455.6 grams and a density of 19.3 grams per centimeter cubed. And just so it's not too confusing, so 1 centimeter cubed is also equal to 1 milliliter. And so here's where you could use your dimensional analysis again. So you could have 455.6 grams, and then we're trying to get to milliliters, and then we want grams to cancel. So you could divide by density, which gives you 19.3 grams on bottom over 1 mil or 1 centimeter cubed on top. And that's one way to approach it. Or you could have taken the triangle trick, covered your volume and seen, oh, I need to divide mass by density. And so either way, what do you get for your answer? So I hear some D's, some nods, looking in the chat. Don't see the chat yet. So D, thank you, chat. So 23.6 milliliters. And then I know you weren't given a choice on sig figs, but of course you can see that 3 sig figs was appropriate from our density. And then sometimes you may see this term come up, which is called specific gravity. But all this is this compares the density of a substance to like another density. And usually it's water, which is kind of silly, but, and of course the density of water is just 1 gram per milliliter. And so if you're comparing, right, a density to that, you would just divide by those and then kind of get the same factor. But this is just more for your knowledge. All right, so I think that was the tail end of chapter 1. Yeah.
When you say to write out your work, you're okay with it being like the 61.5 over 73.2, or do you want to see it written out like that?
It's fine, like for this, if you just divide those. Just as long as I can, follow. So you don't have to write it out quite like this. You could just, again, divide those. So let's look at chapter 2 now. So chapter 2, we're just looking at elements and our periodic table tour now. So we said an element is just a pure substance that cannot be broken down. And so we have our periodic table of elements. So of course these are all our current known elements. And so of course if you notice, I forget which ones are natural. I think up to 88 or so are natural. And then, oh, that can't be right.
Uranium occurs naturally.
Yeah. But some of these are synthetic and then also short-lived. So you can tell that by the mass. So notice how these have masses that are not very accurate. So these are so short-lived that you can't even measure their mass very accurately. That's why they're in parentheses. They also have funny names and could have been changed by now too. Yeah, they're always in flux. So you can tell, right, people, there's like a race to kind of make these unknown elements, and then there's, I don't want to go too down the rabbit hole, but there are like theories too of like other spots of what they call stable isotopes, and so people would be trying to make like even heavier elements, and then of course the race to make it is also the race to name it. So you can tell, like, element 98 was named after California and Berkeley. Yeah.
Nah, but you see, the real trick is to just take 1 proton and like 500 neutrons. Then you got like the heavy out stuff. It's completely unstable. Breaks down in like fractions of a second.
Yeah,
There would be something.
sounds like you're trying to do a fusion or something like the sun. So that would be the real dream if you want to talk about energy.
The sun's actually not very efficient. It's just so massive. It
Yeah,
produces
so-
a stupid amount of energy.
So if you could harness that sun energy, like in the lab somehow, like a mini sun, that would be the way to go. But I don't know that we'll get there. That's very theoretical. And so anyway, so we have all these elements. So let's look at common ones. So elements in the human body. So we are mainly a bunch of water, and then obviously we're carbon-based. So we have a lot of oxygen from the water, some hydrogen, carbon, nitrogen, and then others. So of course we have some essential minerals. Obviously we have calcium, and we also have other small minor minerals. Silicon is another earth-abundant element, so just taking a tour. So nitrogen, oxygen, all those are abundant. And then so compounds, are just now combinations of these atoms. And so there's different ways to symbolize the compounds. So this little red ball represents oxygen, and so this is just water drawn here. And so the compound also has a defined formula, so it'd be H2O. So all this is saying is for every one oxygen, it's going to be bound to 2 hydrogens. So this is a representation of ethane here. So these 2 black balls represent carbon, and then the little white balls all represent hydrogens. And so this again has a defined chemical formula, so C2H6. We also have different kind of ball and stick model ways of drawing these in skeletal structures. So this is more complex, and so not to completely overwhelm you, but we can go over how to interpret this. So each one of these points here, so either terminal or this little like point here, represents a carbon. And so actually let me just redraw this because that'll be easier for clarity. So this is a carbon. And then carbon always has to have 4 bonds. And so we don't always draw in the hydrogens. And so that's what's actually represented. Double bonded to oxygen. That's a carbon here. Nitrogen attached to another carbon, or otherwise known as a methyl group. Sorry, my drawing skills. Woo. So nitrogen, carbon here. So carbon, and then, so this carbon has 1, 2, 3 bonds right now, so it has to have a hydrogen there. It's not explicitly drawn. Carbon, again at that point, nitrogen, and then one last carbon there. So that gives you kind of some idea. And this is an organic molecule. And so that's how those are represented. So again, you don't show the hydrogens attached to carbons explicitly. All right, so let's look at our atomic structure. So looking back at the individual atom. And so all atoms are composed of the same subatomic particles, so they all have protons, neutrons, and electrons. So let's look at what that means. And so the protons and the neutrons, so this is what makes up basically the mass of your atom. And so the mass of a proton is 1.67 times 10 to the negative 27 kilograms. The neutron is about the same. And then so why we say the electron is negligible is it's only 9.1 times 10 to the negative 31 kilograms. So it's, 4 orders of magnitude smaller. So when we look at the mass of an atom, all we care about are the protons and the neutrons. And then so what is also significant is that the protons have a charge. And so the protons are positively charged, and the charge of the electron is opposite of that. So this is considered to be negatively charged. And then the neutron, you kind of guess by its name, has no charge, so it's neutral. Yeah?
Will we be getting at all into the reason why they have electrical charges, or no?
No. So this is kind of what you want to know, just summarize here. And so the mass, what we can kind of assume is just their mass is 1 AMU. And so when looking at this atomic level, and we'll look at how it corresponds to the chart, we say that a proton is 1 AMU, or 1 atomic mass unit, and a neutron is 1 AMU, and an electron, again, is 0. And then we have our charges. So again, we care about their relative charges. That a proton has a +1 charge, an electron has a -1 charge, and then this is just their Coulombic charge, but that is less relevant for our purposes. There's only if you were to care about this and we're trying to calculate something else. So then how do we define elements? So elements, and this is really important, are defined by their number of protons. So if you change the protons, you change the identity of the atom. And so the number of protons defines the element. So if we look back, so I'm trying to find a periodic table that I like. Let's go back to this one, I guess. So we look back, hydrogen, element 1 here, and so this number also equals to our atomic number and our number of protons. So hydrogen, element 1, 1 proton. And so this is, again, called the atomic number, and it is defined by the symbol Z. Oh, sorry, I just saw in the chat. Do we need to know the exact mass? No, we just care about AMU, and again, we'll look back at AMU in a second. And then, so looking at these little depictions here, so now we have a little helium atom, and so in its nucleus, it has 2 protons here. And again, we go back to our periodic table. Let's look. So helium, it's element 2 here, so corresponding again to those 2 protons. And so in this picture, so while we're looking at this picture, what's also found in the nucleus are the neutrons. And so again, those neutrons, we said that the mass does matter, so they're also 1 AMU. So our total mass for helium, right, would be 1, 2, 3, 4 atomic mass units. And then if we look in our periodic table, you notice it has 4 there for its mass. And then your periodic table should also have, that's what I forgot to do. I'll print out periodic tables for lab, so you can have them and annotate them. But your periodic table also comes with a guide, so it tells you atomic number, you have some symbol, and then your atomic mass there. And so let's look at carbon. So again, carbon has 6 protons, and then we can discuss more about carbon later, but carbon actually has some isotopes, and so we'll define what that means in a little bit. And so the elements are arranged in the periodic table by their atomic number, and so they're arranged in increasing atomic numbers, so you can just see that goes 1, 2, 3, 4, 5, etc. But then they're kind of arranged in these funny columns based off of their property. So elements within the same column have very similar physical and chemical properties. All right, so now let's look at, so what are isotopes? So we just mentioned them. And so isotopes are elements with varied number of neutrons. And so, right, we had just finished saying, so the identity of our atom, right, depends on our protons. However, they do not necessarily have the same number of neutrons. And so this is one way to write out these different isotopes. And so from scientifically speaking, we're not quite sure why these different isotopes exist. And then also different isotopes have different stabilities, which we can talk about. So let's skip around for a second. So let's talk about carbon, since I mentioned it. So we have carbon-12, carbon-13, and carbon-14. So how many protons and neutrons does carbon-12 have? So I guess let's start with how many protons does carbon have? So 6. Oops. And then another key point, so let's write this down. So the total mass is equal to our protons plus neutrons. Then by this representation here that I've drawn, so this 12 then is the total mass. So how many neutrons does carbon-12? So 6. And then so what about carbon-13? How many protons? So here is 6. How many neutrons? 7. So 7. And then carbon-14, how many protons? 7. So 6. And then how many neutrons? Oh, 8. So excellent. So again, they all have, right, the same number of protons, so we're just varying the neutrons. But then what's interesting is, again, these isotopes have different, what's called abundances, and then also stabilities. So carbon-12 is the most abundant. And it is also the most stable. And then carbon-13 is also relatively stable, but it just has a low abundance. So it's about 1% abundance. And so this is useful. It has other properties. So carbon-13 is used in a technique called NMR, and you can do a carbon NMR with it. And basically it has certain properties that mean that you can put it in a big magnet and kind of align all the electrons, then relax them, and then it gives you a pretty picture. And you can only do that with, again, the carbon-13 isotope, which means because it's only 1% abundance, this is a hard experiment. Yeah.
So I know that some, like, archaeological bones are determined through carbon. Is it one of the isotopes, or is it something else?
Yeah, so you beat me to the punch. So the dating that you're talking about is with carbon-14. And so why that's used for dating is that it is radioactive. And so, like I was saying, right, we're not quite sure why these different isotopes exist, but we do know that this is slightly unstable. Again, not entirely sure why. You'll see that there's different ratios, but for some reason 8 neutrons is a little unstable, and so it starts spontaneously decomposing. And so like you were saying, it's used for radioactive dating, because basically what you can do is you can measure your known concentration, since I just finished saying, right, they're in a certain ratio. So you could look up the ratio of carbon, 12 to 13 to 14. So they're in a certain abundance. But then if something has died, right, that means that it's no longer taking in carbon-14 and putting it as part of the body. And then it's decomposing, and it's losing that carbon-14. So then you can tell by the ratio how old a sample is. And of course, this is only accurate, to a couple of 1,000 years. I have to look because the half-life is about 5,000. I don't remember the number quite. But yeah, you can measure, somewhat accurately based off of that. So now going back to this neon representation. So this is just another way of writing the isotopes. So they give you the total mass and of course your atomic number. And again, they all have 10 as their atomic number. They all have to have 10 protons, but they just differ in the number of neutrons. So this has 10 neutrons, 11 neutrons, and 12 neutrons. And then, so now this is reiterating that just your mass number is equal to your number of protons plus neutrons. So again, whatever your mass is of that particular atom you're looking at, it's going to be equal to your number of protons plus neutrons. And for this isotope representation, we'd have our mass here, atomic number, and then whatever the chemical symbol is. You could also just represent it like neon 20, neon 22, something like that. Or like I had the abbreviated, 21 neon or. All right, so let's look at this. So what is the atomic number, mass number, and symbol of a chlorine isotope with 18 neutrons? I'll flip to the periodic table since we don't have one. So how would you write that? So what's the symbol for chlorine? We'll start with that. Oh, it's just Cl. So most of the symbols, by the way, they're either one letter or two letters. So you notice it's just one capital letter or then a capital letter followed by a lowercase. It's only these weird ones where they have three, but they don't really. Yeah, those are not normal. So we have chlorine. And then, so what is the atomic number for chlorine? I need to flip back. So good eye. So 17 there in that upper corner. So 17. And then, so what's the total mass? That's 18 neutrons. $35, excellent. That gives you 35. And I see it in the chat as well, thank you. So that's how we could write our 35 chlorine there. Again, you could also write it abbreviated. Any questions on that so far? All right, so let's take a tour of the periodic table. Oh, let me pull up. So I like this periodic table. So we'll just start over on the left side here. And so this is just ptable.com. The only reason why I like looking at this website is now it's not doing what I like it to do. There we go. I like that it pulls up the Wikipedia article so we can take a look at the picture. So starting over on this side, so let's just write. So these are the alkali metals. So all this column here, so generally excluding hydrogen, but all these are your alkali metals, and so they're famous for being water reactive. And so let's go back to our P table. Oh, definitely don't want to see my email. And so these are all metals. And so they're all nice and shiny. And so again, they're very reactive. And so when you look at this nice Wikipedia picture, they're in oil. And so if they were not in oil, they would have this coating of oxide on them. So lithium oxide, sodium oxide, whatever. Oxide, since they react with the water that's just in the ambient atmosphere. Lithium is also kind of funny. This is just a random fun fact. So lithium also reacts with nitrogen to form like this little blue compound. So chemists like work in this thing called a glove box sometimes that gives you an inert atmosphere. And usually things don't react with nitrogen, except lithium does. So if you keep lithium metal in your glove box, it'll eventually take like a little blue sheen to it. And so that's lithium nitride. So then just going down, so sodium, again, also metallic looking. So these are also really soft. So you could cut them, pretty easily with just like a knife. However, once you get down to, so potassium is the last one you can work with in air. And even then, so if you were to take potassium and slice it, it has a chance of auto-igniting in air because of how reactive it is, and it would make a nice purple flame. So anytime you're working with these alkali metals, especially so sodium can be pretty hazardous. Just a fun story. So when I was an undergrad as a freshman, I forgot why we were using sodium, but I was cleaning up sodium, and I thought I had quenched it properly. So you want to react sodium with like isopropanol and stuff initially to get it to react all the way before you like hit it with water. And so I thought it was all gone, and then so I have a like 50-liter waste drum sitting in the sink. I hit it with some acetone, and the whole thing lights up on fire. So like the little beaker I was holding lights up on fire, which then causes the whole waste thing to light up on fire since I was pouring it in there. So that was great. So that was like one tiny piece of sodium that you can't even see set off a huge flame. And so for the safety record, you just cut the oxygen and everything was fine. But again, many fires can happen that way. So potassium, scary. But if you're working with these alkali metals, you would want to have a class D metal fire extinguisher. So you guys, have you heard of like the Teslas, how they catch on fire, right? And they let them burn? So that's why they have lithium in them. So those lithium batteries, once they're on fire, you just gotta let those burn. So those are those. And then so rubidium, you would not be able to handle in air. So I'm sure you can watch plenty of explosion videos on YouTube. And so this is in a sealed ampule. And then cesium, again, you can't work with in air. So now let's look, so the next group, so these are still metals. And so you have your key here. These are all metals. So now these are called the alkali earth metals. And so now they are less reactive than their alkali metal neighbors. And so to get them to go, usually they have to react with like acid. That's how you get them to kind of start reacting. So this is beryllium, which is a fun element. So magnesium, I think we'll get to play with some magnesium. So magnesium, again, you have to hit it with HCl, and then it reacts with HCl. So it would just sit there in water. So calcium, I think this will react with water, but again, not as exciting as these. So strontium, also a fun one. So again, all metal in character, so you can see that. And then, so we'll skip the transition metals for now. Not because I don't like them, they're actually my favorite, but they just have d orbitals and they like to be funny. So we'll ignore them for now. So these are all metals, so transition metals. Although I will say that a lot of your fun firework colors can come from some of these. So cobalt, nickel, copper, and then a quick tour. So this is, I know I lied. So these are the coinage group here. So copper, silver, gold, and then nickel, palladium, platinum. These are like good catalysts. So palladium and platinum are used a lot in like catalysts. All right, so now let's actually skip the transition. So now we have group 3 over here. And so called group 3 because I'm looking at this group 3 here. So looking at our numbering. And so these start to get a little funny in that they are less metallic. Some of these are more like metalloids or semi-metals. So boron is a semi-metal here. So let's look at boron. So group 3 over here, they are all interesting from a chemical perspective. So boron's kind of funny in that, and we'll look more into this, but boron can make either 3 bonds or 4 bonds, and we'll look at why that's funny as we kind of delve more into the topic. But this makes boron a really interesting research subject. So people are trying to do cool transmetallation reactions with boron. You can also make some materials, I think, that they're working on. Gallium is also interesting. So gallium is funny because gallium has a really low melting point. So if you look at it, this little Wikipedia statement, so elemental gallium is a liquid at temperatures greater than 29 degrees Celsius. So it's actually kind of a pain to work with. So if you're like trying to measure out gallium, you're like trying to hold it in your hand and trying to split it apart. It's very obnoxious, but there's also funny like books on it. So there's some book called The Disappearing Spoon, and basically it mentions like a gag where if you have like a gallium spoon and then you start stirring your coffee with it, then your spoon would disappear. I don't recommend that. And then indium, I don't have anything too interesting about indium. And then thallium. So thallium I like mentioning because it is toxic. So thallium compounds are toxic. They can also lead to hair loss. That's one of the symptoms of thallium poisoning. So just fun facts with that. So be careful. So let's move over to group 4 now. So this is kind of of course we have carbon, so we're carbon-based life forms. So the interesting thing about carbon is carbon has a really small radius, so smaller than you would predict, and that is part of why we're carbon-based life forms. And carbon can make multiple bonds as well. I think there was like some article where they thought they had made silicon-based life forms, but I think that was actually a lie. So I followed back up on that, and that was not the case. So they've been trying to make silicon do the same things carbon can, but carbon is just special. And silicon, of course, is semiconductor, so it's used in chips. Then germanium is pretty close to silicon in terms of properties. So again, both metalloids. Then moving down, so tin. So tin and lead start to become more toxic. So tin compounds like organotin, those are toxic. I do not recommend them. So again, you have to be careful with tin. A lot of these organotin compounds can cause like convulsions if you were to ingest them. And then of course lead is also toxic. Lead is also one of those heavy metals, although there are some questions over what is a heavy metal, but we just tend to classify lead as one of those heavy metals since it bioaccumulates. How are we doing on time? Let's see if we can make it through the quick just properties tour. And then, so now let's look at group 5 here. So now we start getting into gases and more kind of non-metals. So let's look at that. So of course nitrogen is a gas. Nitrogen is interesting because we mentioned that we could have, right, liquid nitrogen in those big containers. And do they make like liquid nitrogen ice cream anywhere around here? Yeah. Medford is not cool.
Craving one?
Oh, you could make one. We could do it. I would just have to order us a class doer or something. I'm like not even kidding. But why liquid nitrogen is good for ice cream? So, right, you have your ice cream and whatnot, and then you just want to be mixing it, and then you add in like the liquid nitrogen. But what's nice about it, since it crystallizes so quickly, since of course liquid nitrogen is really cold compared to just making ice cream the traditional way and trying to freeze it, is that it prevents those crystals from being too big. So now you have like a really nice smooth ice cream with the liquid nitrogen. Plus, if you wanted to make it boozy, that's the way to do it with liquid nitrogen.
Isn't that also somewhat similar to like how Dippin' Dots are made?
Yeah, so that's exactly how Dippin' Dots are made.
So they're made like little things. Okay,
Yeah.
who wants to take a field trip to the Rogue Valley Mall to go to the Dippin' Dots machine?
That's way too lame. So we could.
Fine, let's go to the zoo or something. Science works, that's better.
Science works. I'll actually do it in front of you.
Do you have other comments about liquid nitrogen ice cream?
No, just dots.
But yeah, you could make Dippin' Dots too with liquid nitrogen. So you would just dip your ice cream mixture through liquid nitrogen. I haven't made Dippin' Dots, but I have made plenty of liquid nitrogen ice cream. Might have to do that. I just have to see who wants to buy me a doer. And then, so I think we talked about phosphorus before, but phosphorus, of course, now is non-metallic-y looking. So it comes in like powdery form. So we mentioned the different forms of phosphorus, different allotropes. But again, it doesn't look like a metal now. Now it's classified as a non-metal, so you can see our colors changing here. Yeah,
Will we be bringing in some white phosphorus to science class?
no. And then, so arsenic is back under the metalloid category. And then antimony, so also a metalloid. And bismuth. So now let's go in the 3 minutes we have. So group 6, which I also call the smelly elements. And so if we look, so obviously oxygen isn't smelly, but what's interesting about oxygen is, so if you were to condense liquid oxygen, well, first of all, you wouldn't ever want to introduce liquid oxygen to an organic solvent, because that would be a bomb. And so this is a huge danger in like a synthetic chemistry, like air-free chemistry, where you're working with air-free conditions and a liquid nitrogen trap, because again, if you condense liquid oxygen accidentally, you have your organic reaction going, it could be bad. But if you're just condensing liquid oxygen for fun, then it's cool and it's blue. And so that's what it looks like. Then if we go down, so sulfur, usually you don't see it in this crystalline form, but rather powdery. But of course, sulfur, right, is smelly, or at least compounds of sulfur. So sulfur itself, like if you had pure sulfur, shouldn't smell. But what does smell is when it starts reacting and forming hydrogen sulfide. So that smells. Then if we go down, so selenium is also smelly. So compounds of selenium are smelly. And then even smellier is tellurium. So I thought there was mentioned the smelliness in the Wikipedia.
Probably biological.
Yeah, I couldn't find it. Here we go. So if you're exposed to a small amount, apparently you get tellurium breath, which apparently smells like garlic. But I thought there was something else. I'd have to look it up. But I think there was a town that was evacuated because they were making some tellurium compound, and then it accidentally got released, and it was horribly smelly. So I don't advise those compounds. They're fine. And then so polonium, also good. And I think we're out of time, but I guess we'll have to finish because we still have 2 categories. All right, so I guess we're out of time for today. So we'll have to leave y'all in suspense. So the last 2 groups are halogens and noble gases, but we'll go over them on Thursday. Yeah, I will take the homework if you're turning them in person. Otherwise, you can just turn them in online, upload them, and it's fine if they're late or whatever. I had a few comments about the due date of Monday. I just kind of set it as Monday because, again, that's what I did it as. But if it's a day or too late, I'm not looking to penalize anybody. I'm just trying to set us on a schedule. Anyways, I will see y'all in 30 minutes for lab. All right. Thank you, chat. I'm going to be ending the stream.
can
No.
start by doing it online, it's okay.
Yeah.
I can come in for some of them like tonight, but tonight and next week I can't.
Yeah, that's fine. That's why I have the class hybrid, so you can, you know, come in and out as you need or,
That's really nice.
yeah.
All right, thank you.
All right, thanks, Chet. I'm still here in case there are any questions or anything. I'll hang around for a few minutes or so and just leave the stream running. Thank you. Any other homeworks? Questions? Just goggles if you have them, otherwise I think we have some.
Not this thing?
Yeah, we could probably loan you a pair or give you a pair.
A list of questions for the measurements and mixtures lab?
What's
Want
up?
me to bring that?
You can. I was just gonna print out copies for people, cause,
At least you have like that stuff done, that's good.
yeah. All right, thank you again, Chet. Y'all were excellent. I'm gonna shut down the stream as it looks like there are no more questions. So thanks again.